Standard linear algebra behaves like a straight path. When you solve for a single variable, the math leads to one predictable destination. But the moment you add a squared exponent, that single path fractures. The variable multiplies by itself, and the internal logic of the equation shifts. This shift produces a result that seems counterintuitive, one equation that generates two different, equally valid right answers. We are left with a system where a single mathematical statement equals zero in two separate ways. To find where those answers come from, we have to look through three different mathematical lenses: the arithmetic of signs, the logic of products, and the geometry of curves. That tiny exponent changes how we define a solution. It creates a divergence where the math points toward two targets instead of one. Look purely at the mechanics of a square. If we ask what number multiplied by itself equals 9, the first answer is straightforward. 3 times 3 equals 9. But -3 times -3 also equals 9. Squaring erases the original sign, so working backward requires a plus or minus symbol to track both possible histories. This is the specific fork in the quadratic formula where the calculation splits. Since the original sign is lost during the squaring process, the arithmetic requires both possibilities to be listed as solutions. We see this same outcome when we look at the equation through the logic of grouping. Factoring reorganizes a quadratic equation into two smaller groups multiplied together. This triggers the zero product rule. If two things multiply to zero, either the first group or the second group must be zero. Breaking the equation apart creates two independent paths. Algebraic logic yields two roots, because factoring demonstrates two separate ways to satisfy the zero product rule. Finally, we can see this divergence physically by translating the math into geometry. A squared exponent takes the straight trajectory of a normal equation and bends it into a curve called a parabola. To find our solutions, we draw a horizontal line representing 0 through that coordinate plane. As the parabola descends and then arcs back up, the curve must cross that horizontal line exactly twice. The geometry validates the numbers. A curved path crossing a flat plane must intersect at two separate points. These two solutions reflect the physical behavior of objects in the real world. Imagine using a quadratic equation to calculate exactly when a thrown ball is going to hit the ground. The math gives us two correct timestamps for when the ball's height is 0, one in the future at 4 seconds and one in the past at -1 second. The calculation accounts for the entire arc of the curve, projecting a path that exists before the ball was even released. The quadratic equation identifies every moment a system meets a specific condition. We are left with two valid answers, and our own context dictates which one we use.